Welcome, everybody. It's my pleasure today to introduce Primož Škraba, who will tell us about universality and random geometric persistence diagrams.
Thank you, Henry. So this is joint work with Omar Borowski. This is something we've been working on for a number of years now. I think I'm going to try to say too much in the time given, and I may kind of skip certain parts at the end. And I think also people have seen bits and pieces of this, but hopefully there's some new insights that that even if you've seen talks of this on this topic before, hopefully there's something new, and if you haven't, you'll hopefully learn something new. So we'll start off with the motivation. So it's kind of, I think, the most classical motivation in our field, really, which is, if I have some space and some random sample from it, how can I recover the homology from it? And of course, the answer, especially in this seminar, will be persistent homology. The point being, of course, that, even though we know that these points here are sampled from an annulus, we don't know that it is an annulus. We just actually have the points. So instead, we study a function or a filtration bit based on these. And the natural one, and probably the most common one, is the distance filtration. So, we grow balls around the sample points, and at some point, everything fills in. And from this filtration, we get a persistence diagram. So this is all completely standard. And generally, there's some part of the diagram which is actually the answer of the question, right? Which is the homology of the underlying space. Okay, so, I think this is all kind of very standard. I will kind of make a few tangents during the talk. One of them is, we don't actually work with the distance function. We usually build geometric complexes, and basically everything that I'll talk about today are geometric complexes. There are two that are very common, the Cech complex and the Vietoris-Rips complex. Everything I will say basically applies to both. But hopefully towards the end, I'll have some time to kind of highlight the differences in proof techniques, because the proofs, whether you're working with Cech or Rips, can actually be quite different, and the challenges are a little bit different. Okay, so kind of going back to this, here our kind of space is fixed, but there's kind of an underlying bit that's not quite right in this picture, right? Here I have this fixed sample, and we're trying to get some answer, but really the sample it's a sample, it's random, it changes, right? So the thing that we should be working with is not really just this one diagram, and that's something's that we're looking at here, but really, we have multiple samples. So here I have 4 samples of the unit on the unit cube. These gives me 4 different filtrations that I have snapshots here of, and these give me 4 different diagrams. And these diagrams are in some sense similar, in some sense different, but the point being is that they're random, right? So we do need to take this randomness into account, and it's kind of a critical bit to kind of make sure we understand. Okay, so kind of formalizing this a bit, right? We have, for random persistent diagrams, we have some space, we have a probability measure on it. We sample from this, these gives us our random points, and we build some complex on them, again, limited to Cech and Rips. And we build the diagram from this. So this is kind of a standard pipeline. And as we saw before, there's some bit here that has, that's dependent on the underlying space, and some bit here that's kind of due to randomness. So we're going to call this, we're going to call this signal, and we're going to call this noise. Now, how do we actually determine what's signal and noise? Well, usually what we say, right, is something along the lines of, signal is stuff that is far away from the diagonal. And here I just want to take a quick tangent to kind of highlight one thing that will be going on throughout the talk, and that is how we measure what is far from the diagonal, right? So here it's, again, kind of an annulus, H1. That's what this persistence diagram is showing. And usually what we do is we take the lifetime, which is the death minus the birth of each point, which measures how far away we are from the diagonal. Here, instead, we're going to be talking about the ratio. So instead of taking the difference, we're going to take the death over birth. If you really like differences, you can take the log and have a difference. Again, you're still measuring how far you are from the diagonal, but in a slightly different way. Now, the reason we do the ratio, and the reason I'm going to be talking all about the ratio, is number one, this is naturally scale invariant, right? If I increase the death and birth by the same constant, like the same multiplicative constant, it cancels out. On a more kind of less rigorous level, this kind of thing is less sensitive to outliers, right? So in this picture here, what ends up happening is if you want to take this ratio, you will end up needing a lot more points to create something that's very persistent, right? So in this case, this thing is geometrically big, but this thing will actually be more persistent in this death over birth because it's born very, very early. So I will highlight these things, but primarily we'll be talking about death over birth. Okay, kind of going
Primož,
back.
quick question. So Astrid asks in the chat, back one slide actually, does your sample space have a particular geometry? It was back on the slide with the red, green.
Oh yeah, so I will talk more about that.
Perfect. Thanks.
Okay. So I'll talk more about kind of what's the geometry and what isn't, right? So, okay. And actually I was just about to get to that, right? So not just far from the diagonal, but there's another kind of thing that's signal and noise. And the signal, what we really want is exactly the geometry of the underlying space, right? But this part of the diagram ultimately does depend on the geometry, which is very varied and we can't really control it. So instead, rather than kind of focus on the actual signal part, right, which could be pretty much anything, we're going to focus on the noise part, right? So this part down here, which in principle, or actually what I'll make the argument of, doesn't depend on the geometry. And the reason is, there are two ways to kind of go about this, right? You can either try to directly identify the signal, or you can try to characterize the noise and then just subtract that off, right? So it turns out we're doing the second way, right? So we're trying to characterize the noise. And the question behind that is, what is the distribution of this red part, right? So this isn't a new question. People have looked at it. So probably one of the first papers on it is by Hiroka, Shirai, and Trin, who showed that, if you have a point process, this limiting measure exists, right? So if you keep adding points, eventually you will get some sort of measure of diagrams, right? Like your diagram is going to start to look like some limiting measure. Chazal and Devol showed that this measure is a density in some cases. And then, there's been a lot of follow-up work since then. Okay, but, here this is taken from the Hiroka, Shirai, and Trin paper, and you can see that the limiting measures look very, very different because these are different inputs, right? So, okay, so that's really kind of the random geometric diagrams part of the title. The other part is the universal part, right? And what is universality? So I think in our community, it can mean a number of different things. If you look on Google Scholar, there's universal distances. In category theory, there's universal objects. This is very, very different. This is universality in the probabilistic sense. And what this means, first, I'm going to just kind of show two very typical examples of it. So, the two prototypes of it are really the central limit theorem, which is by far the most known, which basically just says that if you take a bunch of random samples, random variables, sum them up, normalize them, you will converge to some normal distribution, right? There's also this semicircle theorem that says that basically eigenvalues of random matrices also converge to some distribution. And the key bits that kind of combines those two is that the output distribution is independent of the input distribution. For central limit theorem, it doesn't matter how the x's are actually distributed, the output will always be a Gaussian. And that's what we mean by universality. So, the big thing, and I think people have seen this before, is, can we find universality in persistence diagrams, right? So this is an example of the Cech in a box, Cech complex on a Klein bottle, in a normal distribution. And, it doesn't look promising, right? So these are kind of the limiting measures of them. They look very different, right? So what if instead of the actual diagrams, though, we take death over birth? So it's a nice scale invariance thing. It has these nice properties. Essentially, we're going to remove one dimension of information and see what we get, right? And if you plot it, right? So these things for each point I take instead of death over, I just take death over birth and sort these numbers and I get a CDF. And if I put them together, it all matches up, right? And these are different geometries, different topologies, different distributions. Okay. And when we first found this, it seemed a bit unbelievable, so we did a lot more experiments, first with the Cech. These are all drawn with multiple distributions on multiple spaces, just with different dimensions and homological degrees, and you can see they all match together, right? I mean, there's multiple lines there in each color. We did the same thing for Rips. It's not quite as nice, but we have some explanation for that. And if you compare the two, again, they don't kind of match up, right? But there is definitely some sort of grouping that's going on. And of course, we didn't just do it for these kind of small models. We did a lot more tests. And there's a paper in Scientific Reports that kind of goes over all of this. Okay, so this gets us, and in the Scientific Reports paper, we made three kind of conjectures. And the first one was weak universality, which says, okay, I fix my ambient dimension, I fix my homological degree, and I fix if I'm using Cech or Rips. And then, it doesn't matter what distribution I have up to some conditions that I'll get into. And I sample i.i.d. from it. I build my persistence diagram and then look at this counting measure, like how many points, like how this is distributed of death over birth values. And we're able to prove actually, so not in the paper, but in a follow-up paper, that this actually holds. So this is a theorem that this limit exists and doesn't depend on the underlying distribution. So this is kind of the key thing that's weak universality, right? It says it doesn't matter what my input distribution is, if the dimension and homological degree and Cech and Rips is the same, the output, this curve, will always be the same in the limit. And this is quite nice, right? Because in terms of characterizing noise and signal, if we don't need to know what the input distribution is, that's very handy for, kind of characterizing the noise. And, a few more examples of experiments, right? So these are uniform, beta, Gaussian. These are the actual diagrams. These are just the ratio diagrams, right? Drawn very nicely, thanks to Omar. And this is just the death over birth density, right? And you can see that they all match up. Okay, so that's weak universality, right? So we fixed all these things. In the paper, in the Scientific Reports paper, we also made we did more experiments and we made another conjecture that we called strong universality. So you take the exact same thing, but now you apply an additional transformation, right? So you take log of these values, multiply by some number and add another number. And the B here is really just really the mean shifted appropriately, and A is just some constant that's depends on Rips and Cech. And if you do this, right, and we look at these curves that I showed before, and you apply these transformations, they all match up, right? So Cech, Rips, all dimensions, all homological degree, it all seems to kind of perfectly fit together, right? So it all fits a single distribution. And then again, we looked and we said, okay, well, if it's all one distribution, maybe we should see if we can fit something to it and maybe get a candidate distribution, some reasonable guess for what it might be. And what we came up with was the left skewed gumball. So this is the CDF of it. And again, here we show experimentally that it is quite a good fit. This is all quite empirical. I mean, we've tried many different things. Not everything fits, but a good number of things do fit. And whenever there is a fit, it tends to be quite good. So, there's certainly no theorem behind it yet, but it seems like this is a good place to start in looking. So just kind of formally, what the strong universality conjecture is, and here it basically says that after this transformation, um, you know, it's independent of the dimension, it's independent of the homological degree, distribution, pretty much everything. It doesn't, experimentally, we even noticed it doesn't need to be i.i.d. Of course, there's no kind of proof behind it, but it's just something we've observed empirically. Is there another question?
Yeah, Steve asks, did you strip out the structure part first? Steve, go ahead and clarify if needed.
No, I think so the question is, so if I understand, it's probably the question if whether there's, if your underlying space has homology and has homology, is this accounted for? So all the things that we did actually, so all the synthetic data didn't have any structure, right? It was the box or some torus or something. I mean, even if it was a torus or something, the point being is there's so few of these kind of signal points that even if you include them, they're not really going to affect anything experimentally. And you can actually even, justify that numeric, like when you're doing the experiments, we also did check that the number of kind of signal cycles was small, right? Because most of the time we knew what it is that we were actually looking for because we knew what space we sampled from. Does that answer the question? Yeah, hopefully.
Yep.
Okay, good. Okay. So, possibly this limiting thing is left gumbel, left skewed gumbel. If you really don't like left skewed gumbel, you can think of it as an exponential distribution with a slightly different transformation. And again, this is all very classical and not very complicated. Okay, so I think many people have seen versions of this kind of experimental talk before. I think they're probably also on YouTube, even if they aren't on AATRN. But so the rest of it, what I want to talk about is basically the proof and the proof of basically weak universality. And the idea here is to give an overview of how it goes. And then if there's time, kind of delve into two specific little things tools that were used that aren't particular, that I think can be done in the time allotted and aren't too complicated. But I will kind of highlight where I'm hiding technical difficulties that are in the paper, obviously. Okay, so the paper is Universality in Random Persistent Homology and Scale Invariant Functionals. And it proves something a little bit stronger than just for persistence diagrams. It basically gives a framework for proving this weak universality for any functional that satisfies certain conditions that I'll get into. But where we started and the main application is most definitely persistence diagrams. So we need to define a functional, right? What are we actually going to be studying? And the one we're going to be studying is the number of points where death over birth is bigger than some alpha, right? So if you look at a diagram, that's all the points that are in this cone here, right? Because as you move up, wherever your birth is, you have to be at least alpha times that birth. D has to be above that. So it's this upper cone. Okay. And initially maybe just in case it's not obvious that this is scale invariant, right? What happens is if you scale your points down, right, all your points move, but the ones in the cone actually stay in the cone, and the ones outside of the cone stay outside of the cone as well. And same thing if you increase it, right? So everything moves, but this cone kind of stays the same, right? The number of points there stays the same. So it is scale invariant. And one of the things that led us to actually writing down the framework is, oddly enough, in the literature, there wasn't very much about studying things that were scale invariant in terms of theorems and techniques. So that was a bit surprising, but that's also why we decided to write it down this way. Okay, so we need 6 properties, right? So the way we do it is it's for any functional, we give a proof that universality holds if it has these 6 properties. So, translation invariance just means that if I move my points around, the answer stays the same. For persistence diagrams, this is relatively obvious. The next one is scale invariance, which I just kind of explained that, our choice of functional was specifically scale invariant. And so that's why we started looking at scale invariance. So obviously persistence diagrams are there, but essentially it says exactly this, right? If I scale things, if I expand my points, right, the answer is still the same. Okay, so these two are kind of, whatever you're studying, in essence, should almost come for free. The other ones are, so the linear scale one is a bit strange, to be honest. Well, it seems a bit strange at the beginning, but essentially you can think of it that if I have these points, the number of points in this cone here, right, is roughly of the same order as the number of points here, right? So if I double the number of points, the number of points should roughly double as well. It doesn't have to be, exactly 1-to-1, but the reason behind this is, again, kind of if you go back to the theorem, we're going to divide the number of points in this cone by n, right? By the number of points that we've used to build this diagram. And if it's bigger, if it grows faster, this ratio will go off into infinity. If it grows slower, it's going to go to 0. So, if you want the limit to exist like we said in the theorem, it kind of has to be linear. Okay. Okay, so that's linear scale. The two ones that I'm going to concentrate the most on are additivity and continuity. So what does additivity mean? Well, it means that, let's say I have these 2-point clouds, right? I can build filtrations on each of them separately, independently. And each of these is going to give me some diagram. But I can also glue them together and build the filtration on both of them together on the union. And essentially what additivity says, it's the property that if I put these two together, like if I just add the diagrams together, the number of points should roughly be additive, right? So kind of formally, the number of points in the cone for just A and just B is roughly the same thing as if you added those two numbers together, the number of points in A union B. Okay. So again, it doesn't have to be exact, but you need some control on how much it can change. Okay. Continuity is kind of a very similar concept, except here now take this box, sprinkle a few points, and again, you need some control on how many points. If I add some number of points, how many points in this cone changes, right? So again, you need some control on how much things change. There's one more in the paper called homogeneity that I'm not going to get into. Number one, it's kind of a technical thing. You don't really need it all the time, but it's, in full generality, you do. So it is in the paper, but for most things, you can actually avoid using it depending on what your particular setting is. So again, it's kind of a very it's not particularly enlightening, so I'm basically going to skip it. Okay, so now moving on to the idea of the proof. So we have these 6 properties, and now how do we prove this, right? Well, we start off with a reference model, and for persistence diagrams, it's always going to be uniform on the unit cube, right? And essentially what you want to say, so the first thing you need to prove is that as the number of points goes to infinity, the number of points in this cone divided by n goes to some limit, right? So it's going to be some portion of all the points are all like the portion of points in this cone is kind of converging to something as n goes to infinity. So that's kind of the first step that you need to prove. And then once you do this, we basically want to say all the other models, whatever other things we use, will have the same limit, right? So that's kind of the proof technique. That's the idea behind it. Okay, so now we don't have uniform anymore, but let's say this little Gaussian thing, right? It's a 2D Gaussian where red is higher and blue is lower. Maybe it's not really a Gaussian, maybe it's compact. It doesn't particularly matter. But what you do is you first approximate this kind of density with a piecewise constant density function. So you can think of it as kind of pixelizing it, right? You make little squares, and in each square, you put a little flat, you put a flat piecewise constant density on it. And, and you use that kind of approximation. You can think about how we, when you teach when you learn calculus, right? When you learn kind of approximating an integral with little step functions, same thing, right? Okay, and why does this help? Well, this step actually is pretty straightforward because we have our reference model, right? Each square is uniform because that's the piecewise constant bit. So each one of these squares has the same limit. And then when we glue it together, because we have this additive property, we don't change very much when we glue things together. So putting everything together into this piecewise constant thing is basically the same thing as the uniform distribution. So that step, is I think very intuitive. And then to get to kind of the full generality, you take each of these boxes and you have a uniform thing, but it's kind of close to this general function. So you only need to sprinkle a few points in each box in order to get to the general distribution. And that's where continuity comes in. And here I'm hiding a lot of technical, this is quite technical to prove, and one needs to be quite careful about how one does it. But the core idea is essentially these three steps. But each of these steps is, of course, quite involved because you need to be quite careful about how you do it. And there's numerous pages in the paper that are dedicated to it. Okay, so that's kind of the main idea. So that's how we get from the reference model to this general density. Now, a few words just about how general the density can be. So we deal with three basic types of density functions. So the first, so here there's the ones with compact support. So there's two types here. One is where essentially it's bounded away from zero on the support. And here, it's actually it can be a bit more general than what's on the archive version. Essentially, if you're bounded away from zero, as long as you have a density, it's fine. There's no other assumptions that are really needed, which is somewhat surprising. But it works. If it does go to zero on the boundary, you need some conditions on how it goes to zero, so that all the calculations work. And then, of course, there's also non-compact support. The way we deal with this is basically we put conditions on the tails. That doesn't mean that it has to be kind of a very nice kind of, that it can only be a Gaussian or something like this, because if in the middle somehow it does something funky, you can always kind of break it up into this compact set and the tails and kind of do the analysis separately. But again, there's a lot of kind of variations you can do here, and there's very quickly you have to do a bunch of calculations from scratch. So these are the ones we chose. There's a good number of things that are actually covered here. But just to say it's not, there are other things that can be proven. It depends on the specific setting. Okay, so that's the general thing. The examples I gave were for persistence diagrams, but the proof technique itself works for any scale invariant functional. So kind of a good part of the paper actually is proving these 6 properties for persistence diagrams. And for the number of alpha persistent points in persistence diagrams. Here, essentially, the first 3 are in a sense easy. Well, the first 2 are certainly easy, right? Because we know persistence diagrams are translation invariant, and we've designed this ratio. I mean, well, we started studying this ratio and noticed that it was scale invariant. So those 2 are easy. The next one, the linear scale, actually did exist in the literature for some of the models, not all of them. But again, it's something that can be kind of done relatively directly, and it is quite technical work, but it somehow, it can be done kind of directly, or it exists in the literature somewhere. So again, the two things that I'm going to focus on are additivity and continuity, because these are kind of, I think, the main kind of new things that really didn't necessarily exist. Now, in both of these cases, right, we're changing our underlying complex, we're adding points. And again, we need to show that things are approximately the same when we do this. So we really need to bound how much diagrams change when we add a point, okay? And I want to kind of go through this in a little bit more detail. So, before we add a point, what happens when we add a simplex? Adding, again, the simplex we add or remove might be anywhere in the filtration. But let's start with an even simpler case, which is what happens when we add a simplex to the end of the filtration. And again, this is something that's quite well known because this is the way we compute persistence, right? We add simplices one by one, and we see, there's some simplices that create a new homology class. We call them positive. Other ones bound in existing class, we call them negative. For each simplex we add, we know exactly how things change, right? It's either kill something or create something new, and it's a change of one, right? So for each simplex, there's exactly a change of one. In case you haven't seen this, it's quite classical, right? You look at the map of adding the simplex to something that exists before, and here's the bit of topology. You hit it with the Mayer-Vietoris long exact sequence, where here I have my previous simplicial complex. Here I have the simplex I'm adding. Here's the simplicial complex afterwards, and the intersection is just the boundary of the simplex. The simplex is trivial, so essentially the fact how this change works because of exactness just depends on this map, right? So it's exactly this long exact sequence, and we essentially just need to look at this map from the boundary of the simplex into the previous complex. And because this is exactly rank 1, there can only be one change. Okay, so this was first, probably even before, but where I know it from is from an old paper by Delfinato and Edelsbrunner. But that's at the end, right? So that's something simple. What happens when we add a simplex in the middle? Okay, and here we need another idea. The Mayer-Vietoris isn't going to work. We have this, again, I guess it's almost coming up on 20 years now, which is quite scary. This paper, Vines and Vineyards by Cohnsteiner, Edelsbrunner, Morozov. And they do a lot of things in the paper, but the ones we're going to be concerned with is what happens when you switch the order of two simplices, right? So I have a filtration, and I'm just going to change my filtration by switching the order of two simplices. And they worked out exactly what can happen. So here, the answer is pairing switches. And here, I've annotated these bars, these persistence bars with these simplices. And, if I move this tau 1 earlier, what ends up happening is that the deaths and births kind of directly switch. So it turns out this is all that can really happen. And there's 4 different cases in which can happen if you do something with an infinite cycle, if a negative simplex moves earlier, or if a negative simplex moves earlier and crosses a positive simplex. These are all the pairing switches that can occur. And this is actually quite a nice thing because it's quite structured in how things can change. We're going to be focused mainly on this one, which is the negative simplices moving earlier. And so what does this have to do with this? Well, what we can do is, right, we can add the simplex at the end and move it backwards to where it really belongs in the filtration. And if you do this, well, okay, at the end, we know it's, let's say it kills something, and then you move it back. Well, there's a pairing switch, and you move it back further, and there's another pairing switch, and you end up with this structure of nested bars, right? And this is what we call a cascade. Actually, this is what Dimitri named a cascade. So whenever we insert a negative simplex in the middle somewhere, we have this cascade, and it has this very nice structure. Now, if we look at this structure in a persistence diagram, right, we're adding this negative simplex, this is the new thing. And in the diagram, so I've annotated it with the actual, births with the little symbols. It just moves down, and it moves down in a specific way, right? It moves down that the new death of this box is basically the old death of the thing that came right before it. And again, I'm not going to prove it formally, but if you look at this, right, because of this structure, there's only one thing that can actually cross, even though any number of them can move, only one of them can actually cross out of this cone, right? Because of this particular structure. So this gives us a lemma that says that, we can bound the change. Now, I haven't said anything about positive simplices, but if you add a positive simplex in the middle, if you kind of go through the argument, you can see that it has to be an infinite cycle or an infinite class, which means that it will add exactly one thing into the cone because it's death over birth is infinite. So we have this lemma, and this allows us to control, if I add a simplex, how many that only one point will change in this cone, which, that's as good a control as we would want, right? As we could hope for, really. Of course, this gives us one bit of control, but what we really need is a bound in terms of the number of points. So how many simplices are added? There's a lot more work still to do. And, additivity, okay, so additivity, I think, is the slightly easier one, right? And essentially what you can end up doing with a lot of analysis is that everything happens kind of relatively near to the boundary, kind of within logarithmic distance of the boundary. So the number of simplices that are there aren't too many, or it's kind of a lower order of magnitude than the total number. And so it becomes kind of a negligible term. Continuity is actually a bit trickier because you're removing, if you think about Delaunay, I add a point, I remove some simplices, I add some simplices, and there are configurations where this can be kind of very big, but you can show again with a lot of analysis that you will never add too many, and actually an expectation is roughly a constant per point, right? So that there's a lot of analysis here, and a good portion of the paper is dedicated to proving these statements, but it's all quite technical, and it's not particularly insightful. One just needs to go through it. I do want to so I think I'll finish in about 2 minutes, really, maybe a few more, but one thing I do want to say, an important ingredient in kind of proving these bounds. So first of all is this notion of critical simplices. And first, so this is where Cech and Vietoris-Rips really differ. So, if you think about Cech, at the end, there's, right, there's 2 to the n, 2 to the n minus 1 simplices, right? Because you end up with the full simplex, or 2 to the n simplices, rather. But we only really care about counting simplices where something actually changes. And in terms of the Cech complex, there's a very nice way to do this. So there's this notion of a critical simplex, right, which obviously changes something, but there's this nice local description of it, which says it's a simplex is critical if and only if its circumsphere, so the circumsphere of its points, of its vertices really, is empty. Yeah. Was there a question? Oh, sorry. And the center of the circumsphere is quote unquote in the simplex, and I'll show you what that means. So here's 2 examples, right? So the one on the left is critical, the one on the right is not. So this is a tool that really Omer is kind of one of his very good tools to have. And it's been used in various other places. So I have one reference here. It's also been used by Adler and Bobrovsky in Morse theory for distance functions, and also Bauer and Edelsberner for Morse theory for Delaunay complexes in different forms. And just so if you need a 3D picture, this is the same picture kind of holds in any dimension. Okay. Again, the idea being is that this is very similar to Morse theory in critical points, and it's kind of a local description of when things change. And once you have some locality, you can do a variety of things with it. Okay, so just to contrast very quickly, I do want to go with that with RIPS, you don't really have this. And so we needed to kind of come up with something that would work. So you don't have critical faces, but you have critical edges, right? Because everything happens when you put edges into the RIPS complex. And if I have this edge here, all the points that I have to be inside this kind of intersection of two balls, right? Because new simplices have to include this edge, and so they have to be close enough to both points. So there is some locality, and there's other things like, for example, it can only be critical if, so there's not if and only if, but if this region, this little I region is empty, and for reasons I'll kind of get to in a second, if there's a point in here, everything is kind of close to this point, and you can kind of show that nothing will actually change. The other question, of course, is how much can actually change with one edge, and in what dimensions, and this is kind of the other bit. And the idea behind it is actually exactly the same for what I showed before with one simplex, right? With Vietoris, you take the edge and everything you've added and everything that was before, you build a long exact sequence, and there's a term, basically this closed star of the edge that drops off, and you end up with this kind of quite nasty thing, but it's defined inside this region and it kind of controls everything. Right. And so you again have some control, and in the paper you can actually take it a step further and kind of repeat the process again and get this quite nice bit in terms of the link. Okay, so the things that kind of wraps up for the content, but just to kind of wrap up, things I didn't get to are other scale invariant functionals. There's some in the paper. There's many other ones that one can study. We did do some experimental work and some preliminary things on clustering. So there's a universality for kind of H0 as well. We haven't explored that fully by any means. We have two postdocs that are kind of extending these weak universality results. One is Uzu Lim, who's extending it to more general spaces. So everything I've said is in Euclidean space. And Parker Duncan, who's kind of showing that actually not just these whole distributions, but also just the biggest cycle. So if you take the maximum over each diagram, it also is in a sense universal. And of course, I haven't had time to talk about any applications as such. And so with that, I'll really kind of finish with just the parting thought that, we have weak universality. It's a theorem. There's a lot of things kind of still to say. Strong universality, we're still unfortunately very much at the conjecture at the conjecture phase. A lot of open questions. I will say this, if you are in an application, the one thing that's very easy about this, if you compute a persistence diagram, it's very easy to check. You just do the transformation and you can just look whether it looks like Gumbel or not. So with that, I'll finish, and apologies for going a few minutes over.
No worries at all. So before we get to questions, let's briefly unmute ourselves and applaud for Primož. All right, questions.
Hi, can I ask a question?
Yes, please.
Hi, thank you for a very beautiful talk. I wanted to ask, have you worked looking for any quantitative results? I mean, results of the type comparisons between your limiting distribution and your empirical distribution in terms of Wasserstein distance or some similar metric?
So the way I would phrase that, and let me know. So basically, if there's any notion of convergence rates, is that about
Exactly,
right?
exactly.
There's, not for this full functional. I mean, it's something, let me put it this way. It's on the list of things to look at. There's some notion that one can say it's not the things that can be said right now about convergence aren't terribly satisfying, but they aren't terribly tight either. There's a few kind of very technical issues with kind of doing it, kind of proving these convergence rates. I mean, it really is this kind of technical bit there's something in the diagrams that's quite hard to localize kind of quantitatively over the entire diagram, essentially. Because if you wanted a convergence rate, you would need a bit stronger kind of localization to kind of, that cycles kind of aren't too big in a sense, and they aren't, but getting a nice quantitative bound on it is still kind of out of our reach. Uh, but it's definitely there, and it's definitely should be, there definitely should be results that say something along these lines. It's just technically difficult.
Okay, thank you.
Further questions? So I want to ask a question. So before you went to Gumball, you explained how, say, in the Cech case, you have these different curves that change slightly depending on the dimension. I mean, if your space was if your probability measure had some like fractal dimension, could you potentially detect like a
So, I mean, yes and no. I mean, yes, I think, well, I think the answer a priori should be yes. But, honestly, for fractal, there's enough there's enough things to give me a pause whether the theorem applies to it as such. I think you can probably do it in a way, but it would be quite. I don't think the theory as written kind of applies, right? So I think in practice, actually, it probably just works. Um, I mean, we've done experiments, and essentially, it seems like this average value is essentially giving you exactly the dimension for, like, there's some curve. If you fix the homological degree, it looks very much like it's there. In terms of proving even like the weak universality um, for fractal spaces, I think, I think it can be done, but I think it's not technically trivial. So, for the intermediates, so like for the intermediate spaces, for example, like we did try stratified spaces, and you do get kind of, if I sample something from this dimension and something from this dimension, I get kind of the convex combination. So there is that. Uh, and again, Uzu is kind of moved that forward and proved a lot of it. But again, yeah, for fractal, I would expect you would need some sort of very complicated, dyadic decompositions that honestly seem like a headache.
Right. So there's a question in the chat, and Maxime can't conveniently unmute, so let me read it. It says, "Thank you for the amazing talk. Have you considered a square of your statistic, namely death time divided by birth time squared? It's scale invariant, but with B and D having a meaning of metric scale, just like STD-S. The square would be seemingly similar to a ratio of variances. These are often F distributed, F for Fisher. I wonder if that could be modeled with something simpler than L Gumball."
Yes, we have looked at it, not necessarily squared. Actually, we looked at death over birth to the dimension D, like where to the ambient dimension. And it seems like that has a similar effect of, taking into account kind of lining up the curves in a very similar way to strong universality. The number of experiments we've done along there aren't nearly as extensive. It's certainly something, again, empirically, we've looked at it, understanding, I think for this, right? So even this square, well, no, so for the square, it's probably not, this framework doesn't apply exactly, but can probably be, it might be possible to adapt it for the weak universality. I'm not 100% sure. Again, I don't think it's completely trivial, but again, we are looking at kind of things like this in an effort to try to get some sort of foothold into strong universality, because it's quite a tricky thing to even try to compare things of different dimensions. you know, we've tried various things. There's nothing really to report at this point, but yeah, so empirically, it seems like, you know, it fits very, we haven't tried to fit the distribution, to be fair, but we have tried these various different functionals, and they do seem to have kind of similar information. Again, I don't know, I don't have anything concrete to say beyond that. It's, you know, experimentally, it seems very interesting, but we don't have any theory to kind of follow it up.
Good. Yeah, thanks. Further questions? I had another question. So I agree with you that to separate signal from noise, you want to understand the noise as well as possible. Are there settings where you might be prescriptive, like use universality or related ideas in certain settings to actually try to do this separation?
Well, I mean, so in the scientific reports paper, we give like hypothesis testing versions, right? Where if you're given a diagram, essentially you can test, like assuming strong universality holds, right? You can test whether something, what the probability of, you know, a cycle being this persistent is. You can do this. We've looked at some other things as well, where if you have some, you know, in principle, you could also kind of say, if I have a very ordered system that doesn't have this kind of universal behavior, right? In essence, kind of distance to this distribution tells you how, the further away you are, in a sense, the more ordered you are. So there is some measure that can say something about that, but beyond kind of the observation that it seems to be, that there seems to be something there, I can't really say anything more concrete than that.
Great.
Yeah.
Fantastic. Any last questions? All right, if not, let me stop the recording here.